So welcome to Everyday Mathematics. Today we are still on the 2024 University of Florida Integration B, still on the qualifying round, part 3, and the problem of focus today is problem number 27, where we look at the integration from x equals to 0 to x equals to 1 of fx, where the function f turns all the ones into 0 ones when written in binary. For example, as we can see here, if you have 0, 1, 0, 1, where we have 1, that turns to 0, 1. Where there is a 0, nothing is done, but where there is another 1, we see 0, 1. So this is a very interesting problem, and it feels like now we are in this amazing phase or space where we are integrating in the binary space. So I hope you stick around and you see how we're able to solve this problem. It's very interesting and intriguing, and we are going to say, yay, finally we are integrating in zeros and ones or in binary. Okay, so before we jump into the solution to this problem, I'd like to encourage those of us who haven't subscribed to our channel to please consider subscribing to our channel. Here at Everyday Mathematics, what we do is we solve these very cool problems that we go about and around looking for, and we share with you the solution. If you do like what you see, please don't hesitate to leave a like. But also, if you know somebody that might benefit from what we're doing here, please do endeavor to share this video with them. So without much ado, we're proceeding forward to the solution phase of this problem. So the very first thing we'd like to do is we'd like to ask ourselves, what is binary? Right? For those of us who have done elementary mathematics, and I've covered something related to bases. Binary is simply numbers expressed in base 2, right? And so when a number is expressed to a base n number expressed in a base small n can only bear digits or can only have digits expressed up to n minus 1. And we'll give an examples, right? Examples. Numbers expressed at base 2. The digits AI can only be members of the set 0 and 1, right? And base 3, digits, and this I is just the index, can only be members of 1, 0, 1, 2. And so on and so on and so on up to base 10, where we say the digits can only be members 0, 1, 2, 3, all the way up to 9. So with this in mind, we would like to show something, relationship between, because we commonly express our numbers in base 10, so we like to show a relationship between a number in base 10 and the corresponding value in base 2. So let's say, for example, we have a natural number, and that's positive integer. That's the same as a, and this is a digit at the 0th position, times 2 to the base to the power 0 plus a to the 10th position, the second position rather, plus a2 times the 2 plus all the way, so which is equals to summation from n equals to 0 to whatever point, let's take that to be infinity, of an times 2 to the n. What about a real number that also has decimals to it? So these are positive real numbers. So we could begin from negative infinity, right? To infinity of an times 2 to the n. And when n is negative is when now you have the decimals. So this is just a by the way, but let's now go to the meat of it all. So our integral is from 0 to 1 of fx. And so what we see here is that fx is greater or equal to 0 or less than 1. Another way of looking at this is that x is in this interval 0, 1, right? So in binary, you could have a number like 1, 0, 1, which is the same as 0 here times 2 to the 0 plus 1 times 2 to the power negative 1, 0 times 2 to the negative 2 plus 1 times 2 to the negative 3. And so this is the same as, obviously this we see as a half plus 0 plus 1 over 8, right? Which is equals to 8, 4 plus 1, which is 5 over 8. Okay? So that's a way of looking at it. Now, we say that f turns ones to 0 ones. So for example, f of 0, 1, 0, 1 is equals to 0, 0, 1, 0, 0, 1. Okay? So in other words, x, which is equals to 1 times a half plus 1 times eighth is converted to 1 times a quarter plus 1 times 1 over 16. In other words, what this is doing is that it is dividing x by 2. And so let me express it in a better way here. So what we're doing here is the process is dividing by 2. In other words, we are bit shifting this. That's what we are doing here. Okay, because we see half has been divided by 2 to a quarter. 8 has been divided by 2 to 1/16. So let's now do something here. Let's divide this into 2 intervals. So we'll have x in the interval of 0, 0.5, and then x in the interval 0.5 to 1. We'll divide it into those. Let's say in the interval, in the first interval, in the interval 0, okay, in that interval, what we realize is that x could be expressed arbitrarily as 0.0, A1, A2, A3, all the way. And A1 could be 1, A2 could be, so it could be, the AIs could be, well, let's just say AI is one of that. So what is fx? Fx is going to be 0.0. If L1 is 0, this is still going to be 0. If L1 is 1, it's still going to be 0. So let's just do that. And still Vi is right. Now, what do we see here? Let's do something. What is 2x? 2x is equal to 0.A1, A2, A3. It shifts the bits this other side, right? And what is fx? F2x. F2x is going to be equal to 0.0 B1, B2, B3, and so on. And so what we can see here is that fx dividing by 2 means we're shifting. Fx is equal to f2x divided by 2. But in this interval, because what happens is that this part here is the same as this part, and since this x here, when we plug into fx, we have 2 zeros here, and mark you, we have 1 0 here. When we multiply 2x by 2, if we multiply x by 2, it shifts a1 to this first position. And that means that f of 2x means that the b1 comes to this position. But now, how do we obtain fx from f2x? If you divide by 2, then it shifts this position, this b1, to this position. And so this is an important expression for us. Okay? Now, in the interval, x can be expressed as, because it is 1, so 0.1, let's again use A1, A2, A3 all the way. And so fx is going to be equal to 0.01, and then we can do b1, b2, b3, like that. What about if we did 2x? 2x is equals to 1 point A1, A2, A3, and so on. Now this 1 has crossed this decimal point, so what about if we do 2x minus 1? This is the same as 0 point A1, A2, A3, and so on. So what do we do next? What do we do next? What is f of 2x minus 1? Now, it's very crucial for us to observe that when x is 0. If x is 0.1, A1, A2, this B1 here we don't know whether it's a 0 or a 1, but it shows up right after the 1. So in other words, this is the same as 0 point B1, B2, B3, and so on. So fx, therefore, is equal to this part here, 0.01 plus 0.00 B1, B2, B3, so on, which is this guy here divided by 4. First shift here and then shift here. So this is 0.01 plus a quarter times f of 2x minus 1. So this is good. We have this part here. Very important for us. So in other words, our integral, which we can equate to I, is equal to the integral from 0 to 0.5 of fx plus 0.5 to 1 of fx. So what did we see here? We saw this to be f of 2x over 2. And here we saw 0.01, which is the same as a quarter of 2x minus 1. So if you, in case you're wondering, this 0.01 is the same as 1 times a quarter. This is in binary. So therefore I is equals to 0.5 f2x over 2 plus 0.5 to 1 a quarter plus a quarter f2x minus 1. So I would like to separate this into two separate integrals, just color coding. Let's have blue 0.5 f of 2x over 2 dx. We can use some green here. 0.5, a quarter plus a quarter. Okay, so let's deal with the blue integral first, right? So let u be equal to 2x, and therefore du dx is equals to 2, and therefore du over 2 is equals to dx. Important, when x equals to 0, u equals to 0. When x equals to 0.5, u is equals to 2 times 0.5, which is 1. And so, in other words, 0.5 f2x over 2 dx is equals to 0.1 f of u over 2 du, which is a quarter So this is a quarter I. Okay? Then the green integral, which is integral from 0.5 to 1 over a quarter plus a quarter. Which is equals to a quarter to 1. It's a quarter. This here, let's just continue. So we have a quarter is a quarter So this is a half, a quarter times a half plus a quarter. This is an eighth. But here we can say let y be equal to 2x minus 1. So dy dx is equals to 2. Dy over 2 equals to dx. Important bit. But also we can say when x equals to 0.5, y is equals to 2 times 0.5, which is 1 minus 1, which is 0. When x equals to 1, which is 2 times 1 minus 1, which is y is equals to 1. So in other words, we have 1 over 8 plus a quarter, 0 to 1 f of y dy over 2, which is 1 over 8 plus these two can come out here. So we have 1 over 8, 0, 1 fy. And this also is the same as I. So essentially what we're seeing is that we have I is equals to a quarter I plus 1 over 8 plus 1 over 8I. So this is I equals to 8, 3I plus I plus 1 over 8. No, 2, sorry. This is 2. So we have 3I over 8 plus 1 over 8. Subtract both sides. We have I minus that. We have 8I minus 3I over 8 is equals to 1 over 8. So we have 5I over 8 is equals to 1 over 8. Cancel. So we have 5I equals to 1. And therefore I is equals to 1 over 5. And that is it. So in essence, the integral from 0 to 1 of fx is equals to a fifth. And that's the answer. You know, very interesting. I have a feeling if we did write a program to compute that, would come and then use maybe the trapezoidal rule to calculate the area under the curve, would still come back to a fifth. But I think that would be too much, or be beyond the scope of this video. So until next time, bye bye and be blessed.